This is ME333 Mechanical Measurements. This is our project on inertial measurement units, otherwise known as IMUs. My name is Megan Austin, and my project partners are Rafael Valbuena and Jake Larson. IMUs measure linear acceleration using accelerometers and angular velocity using gyroscopes to give information about the mechanics of the human body, such as joint angles, body center of mass, segment kinematics, and segment global position. And to the right, you can see a picture of a single IMU. It is one unit that makes up a system of about 17 IMUs, and it's placed on various positions on the human body. Common uses for IMUs are injury prevention studies for athletes, personnel rehabilitation programs, animating characters for movies and video games, wearable solutions such as Fitbits and smartwatches, and ergonomics, which is defined as human sufficiency in a working environment. To the right, we have two photos. On the left is a student wearing the Extend system with the 17 IMUs in various places on his body. And to the right is a professional athlete wearing the same system out on the field playing soccer, and his animation will be used in a video game called FIFA 16. The Extend's MVN system has 17 IMUs, and each IMU has 3 gyroscopes and 3 accelerometers. In the figure to the right, we can see the body frame, and the body frame is made up of the femur, the tibia, and the foot. And the position, velocity, acceleration, orientation, angular velocity, and angular acceleration of the body segment are all calculated in reference to a global frame G shown here. The global frame is created during calibration. On the left, we have a figure skater wearing the Extend suit as she skates, and on the left we can see the model in the Extend software. The joint kinematics come from an internal musculoskeletal model based on the joint angle descriptions assigned by the International Society of Biomechanics. Basically what that means is when she wears the suit and does the action, we can see her every move through the software, and the software produces a graph of her right hip joint angles as she skates. These are the components of the Extend's MVN system. And it's important to note that the Extend's MVN system is the system in which we're talking about in this presentation that is made up of the IMUs, the bodysuit, and the software. So the sensor is the accelerometer triad and the angular rate sensor triad. The transducer is the Awinda station, which is this here, and it takes the signal from the IMU sensors and converts it into useful information that we can see through the software on the computer. The signal conditioning is done through the computer software, and the output is the position, velocity, and joint angles, which are shown through the Extend software. So to the right, we can see a snapshot of what the software looks like, and we have the body model here, and below is the right knee joint angle of the body model. IMUs are generally less accurate than traditional infrared camera-based motion capture systems. In order to improve accuracy, the system has a custom-designed signal processing pipeline, which ensures elimination of errors due to aliasing and high-frequency noise. The digital low-pass filter is applied to prevent aliasing of signal while downsampling the signal in the digital domain.
After speaking with engineering representatives from the Extend's company, we discovered that the actual calibration process of the inertial measurement unit is a confidential trade secret. However, we were informed that the calibration process essentially combines the 3 separate accelerometers and gyroscopes from functioning as 3 separate units into functioning as one working unit. During the calibration process, each inertial measurement unit is individually calibrated across an unspecified temperature range and is supplied with its own unique calibration report consisting of parameters that correct for temperature effects, scale factors, bias, misalignment, and G-sensitivity errors, offset, as well as many other uncertainties. The second calibration, which is performed when using the Extend system, is the model calibration. This calibration collects data from the IMU sensors to calculate the sensor to body alignment and body dimensions, and then takes this data and updates the model to reflect the real-time calculations. When attaching sensors to a body, the initial position between the sensors and body segments is unknown. Moreover, the assessment of distances between body segments is difficult by numerical integration of acceleration because of the unknown initial position. In order to find the initial position of these sensors, we can use 3 separate calibration exercises, which are the hand touch exercise, the T-pose exercise, and the in-pose exercise. In these 3 exercises, the orientation of the sensor module with respect to the segment and the relative distances between joints are determined in order to express segment kinematics in the global frame. In summary, this helps us establish a connection between the input from the sensors to the output that we see in the computer as a musculoskeletal model. Here, we can see the manufacturer's provided uncertainty sheet for the XN's MVN system. When in a static position, the uncertainty is given as less than 0.5 degrees. So for the z-axis, any rotation about that will be within 0.5 degrees, and for the rotation about the x or the y-axis, the uncertainty is given as 0.2 degrees. In dynamic situations, however, the uncertainty is presented as plus or minus 1 degree. An example of where this would be useful is if we were measuring knee joint angles, which are commonly used in injury prevention. We can expect this measurement to be accurate within plus or minus 1 degree.
Lastly, we want to talk about IMUs at Valparaiso University. Recently, a 16 sensor system from XN was purchased for about $12,000 by the College of Engineering. It's worth saying that this is less than 20% of what it costs to equip the Human Movement Research Lab with infrared motion capture cameras. This is one of the advantages of the IMU system for motion capture. It's much cheaper. This system is available for research in biomechanics through the Human Movement Research Lab. Students from the Human Movement Research Lab are conducting a research program that will study the accuracy of this system more in depth and compare it to our camera-based motion capture system. Thanks for listening to our presentation.